The same way as we have derived the equation of motion in one dimension, we're going to do the same thing and derive the equation of motion in two dimensions for a free fall or projectile motion example, which means that we are going to derive similar equation as in one dimension, but this time we're going to derive the x component and the y component. So we're going to start exactly the same way with the definition of acceleration. A is equal to dv dt. But this time we're going to break this up into two, the x component and the y component. So we're going to first do the ax, whoops, and then the y component. Ay is equal to dvy dt. So this is like reducing our 2D system into a one-dimensional system. So I'm going to drop the vector notation and I'm going to do everything in scalar. So let's do the x component first. I will start with ax is equal to dvx dt. Same way as before, I'm going to multiply both sides of the equation by dt. Since dt is non-zero, and I will end up with ax dt is equal to dvx, which I will then integrate. Same as before, when I reach this step, I need to ask myself the question. The only way that I can integrate the left-hand side is either ax is a constant, or ax is a function of time. Now remember, we're doing projectile motion, which is our free fall example, but in two dimensions. Therefore, the only acceleration present is our favorite g, which is minus 9.8 in the j direction. Therefore, there is no acceleration in the y direction, which means that ax is equal to 0. So for the case where ax is equal to 0, this will become 0 dt is equal to dvx. Similarly as before, we're going to start putting the initial condition first. T is my variable, so I'm going to use t naught. Again, we're going to start our stopwatch at t is equal to 0. And vx is going to be our initial x component. Now let's go back to our diagram and let's imagine we give it an initial velocity v naught. So a particle has an initial velocity v naught and the initial angle will be say theta. Let's imagine that v naught and theta are given to us. That's going to be the angle at which the projectile will be shot. From there, we can easily decompose this initial velocity as v naught x and v naught y. So the same way as we have decomposed vector previously, we can decompose v naught as v naught x plus v naught y. And we can even get the functional form of each component using our favorite right angle triangle, and we obtain that the magnitude of v naught x is nothing else than v naught cosine theta. Similarly, the magnitude of v naught y is going to be v naught sine theta. So now we can use this initial condition and replace it in our explicitly in one of our lower bound of integration. So instead of using v naught, I'm going to use directly v naught cosine theta. Similarly, I need to fill out the born, the top born. I will put my variable here. I have a vx here, so I'm going to put vx here. And again, I need to change my dummy variable to, for example, dvx prime. Same way on the left-hand side, t is my dummy variable, t is my variable. I'm going to change its name, and I'm ready to integrate. Right-hand side, will give me Vx prime evaluated between Vx and V naught cosine theta, which will then give me Vx minus V naught cosine theta. And the right hand side is just going to be 0. Therefore, this gives me, as I move this term on the other side of the equation, Vx is equal to V naught cosine theta. So this is the functional form of my velocity in the x direction in terms of the time, which is my variable. By looking at the functional form of this results, I can see clearly that the x component of my velocity is v naught times cosine theta, which are two parameters given to us initially. Therefore, those two parameters, or those two variables, will not change, which means that Vx is constant, which we already knew because we already made the assumption at Ax equal to 0. So this confirms our assumption. This means that as soon as we launch this particle with the initial velocity v naught at a particular angle theta, at every time and all time during this trajectory, the Vx component will always be the same. And its magnitude will be the exact same one as the one he had originally, because there is no acceleration in the x direction there to change its magnitude. So it all makes sense. Good. Let's move to the y component. A is equal to dv, dv dt in the y direction, ay vy. Similarly, I will multiply both sides by dt, which will give me ay dt is equal to dvy. Here we have to ask ourselves the question, what is y? I can only integrate the left-hand side if ay is a constant or ay is a function of time. Now we're doing again free fall or projectile motion, so we know that there is an acceleration in the y direction pointing down and whose magnitude is 9.81 meters per second squared. And we used to call it g. So in our case, the magnitude is minus g, and the minus comes from the fact that the direction of this vector is going down, which is opposite to our coordinate system. So let's replace ay by minus g, and we end up with minus g dt is equal to dvy. Let's plug the initial condition. T initial is 0, vy initial is vy naught, which we have calculated earlier as being v naught sine theta. Then we're going to replace the top borne by the variable vy. Therefore, I'm going to change that one, t prime. Good. Now we're in good shape. Now we can integrate. Right hand side is trivial. Vy prime evaluated between vy and v naught sine theta. The left hand side, minus g is a constant, so technically I can take it out. So this is similar to minus g between 0t dt. We know how to evaluate this. This is just t minus 0. Therefore, as I move, oh wait, I'm going too fast. So minus g. Here I'm going to end up with vy minus v naught sine theta. So as I move this term on the other side, I end up with vy is equal to v naught sine theta minus gt. And this is the equation of motion of the y component of the velocity as a function of time. Let's look at this equation. This is telling us that as t is equal to 0, this term is 0, this one. Therefore, the y component of the velocity initially is v naught sine theta. We knew that, so good. A second later, at t is equal to 1, then vy will be v naught sine theta minus g. So the velocity magnitude will decrease. and we expect this naturally because the particle goes up, therefore the velocity is going up, which is against the direction of the acceleration, so we expect its magnitude to decrease. Eventually, as t becomes a big value, bigger than 1, and depending on the magnitude of v naught and theta, at some point, this term will become bigger than this term, and the velocity vy will become negative, which correspond to the part of the trajectory where the particle is coming down, the negative sign indicating the direction which is opposite to our positive y assumption of a coordinate system. Okay, so we've just derived the velocity functional form on the x and in the y direction. Let's keep going one more step, and let's obtain the equation of motion of the position in both x direction and y direction. So for this, we need v is equal to dr dt, which will be broken up into two components. Vx is equal to dx dt, and independently, Vy is equal to dy dt. Again, I'm going to drop the vector notation, and let's start with the x component. So I have Vx is equal to dx dt. I'm going to multiply both sides by dt, so I end up with Vx dt is equal to dx, and I'm going to integrate both sides. At this point, I need to ask myself the question, what is Vx? It needs to be either a constant or a function of time, because I have dt in my integration. But we already have derived dx. It was this guy. Vx was equal to v naught cosine theta. And v naught is set initially at t is equal to 0, same as the angle. Therefore, this is a constant as far as the variable time is concerned. If it's a constant, I can plug in here easily. I can even take it off the integral. So I would end up with v naught cosine theta dt is equal to dx. I'm going to plug my initial condition, t is equal to 0, and x initially is x naught. Then I'm going to put my variable on top, change it, t prime. Let's integrate those two, easy integration. I'm going to obtain v naught cosine theta. This will give me t minus 0, and this will give me x minus x naught. So as I move the x naught on the other side, I end up with x is equal to x naught plus v naught cosine theta times t. And this is the functional form of my equation of motion, specifically my position as a function of time. Again, let's look at this equation. At t is equal to 0, my position is x naught. No problem. As t increases, I can see easily that my position will also increase, and it will increase linearly as a function of time. Because this looks like a linear equation. So this is telling me that the change of position in the x direction is going to be linear. That is, at every second, I'm going to increase my position at the same rate. Okay, so that was the x component. Let's do the same thing with the y. The same way as we started with Vx is equal to dx over dt. Now we're going to attack Vy being dy over dt. I'm going to multiply both sides by dt, so I end up with Vy dt is equal to dy. Now Vy, what is Vy? Ooh, boop, 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 bang, up. We got it already. Now Vy is obviously a function of time. Ooh, whoa. I forget how that goes. This? V naught sine theta minus gt. Yeah. Okay. So Vy is a function of time. Good news. I can plug in here and I can integrate. So I end up with V naught sine theta minus gt dt dy. Again, I can plug my initial condition. Y will give me y naught, t will give me 0, variable on the top, y give me y, t is t. And I'm going to change my dummy variable. Okay, good. So let's integrate this. The right hand side, no problem. We've done that hundreds of times. Right hand side. It looks a little bit messy, but again, t prime is my variable. So as far as t prime is concerned, everything else is a constant. V naught is a constant, sine theta is a constant, it was set initially, g is a constant. So really, this is nothing different from, let's say, 3 times sine of 45 minus 10 x dx. And we can do that from calculus. So we can use the same technique. This is just a polynomial of the first degree. The first term will give me v naught sine theta times t. The second term will give me minus g times t to the power of 2 multiplied by 1/2. So let's do it carefully. V naught sine theta times t, then minus g times 1/2 t squared. So this is my left hand side, which I need to evaluate between 0 and t. Right hand side, same thing, y prime, evaluate between 0, y and y naught, which will give me 1 minus y naught. As I evaluate my left hand side, every time I see a t prime, I'm going to plug a t, minus every time I see a t prime, I'm going to plug a 0, so the lower one will give me 0, then the only term that survives are the two first terms as I evaluated them with t. So I'm not going to write the last two terms. This will give me v naught sine theta t minus 1/2 g t squared is equal to y minus y naught. Again, the two other terms here are equal to 0 as I plug my 0 to t and t prime. Okay, let's move the y naught on the other side, and I will end up with y is equal to y naught plus v naught sine theta t minus 1/2 gt squared. And this is going to be my equation of motion of my position in the y direction. Now, if you look at this equation, at t is equal to 0, my y is equal to y naught, no problem. Now, at t is going to be bigger than 0, we see that the y position will increase, as initially this term will be bigger than this one, but as t start getting bigger and bigger, this little power of 2 will start to have more effect. Therefore, this term will be bigger than this term, since this one is negative, then the position in the y direction will start to decrease again and will be in this range. Okay, and this will look like a parabola. Okay, so let's summarize. We have derived four equations of motion. First one was Vx, that give us V naught cosine theta. This was obtained because we made the assumption that Ax was 0. Therefore, it is expected that if there is no acceleration in the x direction, the velocity in the x direction will not change. Therefore, at all time, the x component of the velocity is a constant, which is V naught cosine theta. We did the same thing with Vy, and we ended up with V naught sine theta minus gt, where we used the fact that Ay was minus g. This was, again, a linear equation, so the velocity y at t is equal to 0 is given by V naught sine theta. As the time increases, the velocity, the second term, will be smaller than the first term, so the velocity will still be positive, but it will become smaller and smaller and smaller, because the velocity goes up in my particular case against gravity. If you wait long enough, t will be big enough so that the second term will take over the first term, then v naught, then vy will become negative, and that's when the projectile is falling down again. If, for example, you were just dropping an object, then the v naught magnitude would be 0, which means that the first term would be 0, and right away you would have a negative velocity, which makes sense because as you let an object drop, it's going to fall down. If you still assume that your coordinate system is y positive, at all time your velocity in the y direction would be negative, and it will be increasing linearly every second as a function of time. And then the two other equation were x is equal to x naught plus cosine t. Uh, yep. Okay. Sorry. Uh, Again, this is a linear equation, and this gives us the position in the x direction as a function of time. And then the last one was the y component, y as a function of time, which was y naught plus v naught sine theta t minus 1/2 gt squared. So those are the four equations of motion of the velocity in both x and y direction and the position in both x and y direction as a function of time, which means that if we know the initial condition, we can predict the position and the velocity of that particle at all time, which is nice, which is real nice.